Great. So the group can start, right?
Good afternoon, sir. Good afternoon, colleagues. We the members of Group 2, and the members are Divya Kisunram, Nadir Prasad, myself, Bibi Morazina Mohabir, Manisha Lakan will be presenting on limason, cardioid, and spiral. So, in our outline on the subtopic limason, we'll be looking at the history, application, types, graphing, and area. Now, just to give a little brief history on limason, Um, the limason was first studied in the 17th century by a French mathematician, Etienne Pascal, who was the father of Blaise Pascal. Later on, we had this guy by the name of Gilles de Roberval. He explored the curve in more depth, and the name limason comes from the French word for a snail. And the reason why is because the shape of this limason, this is the shape of a limason. It actually resemble it actually resembles the shell of a snail, as you can see here. If you have ever hold one or seen one in life, just think about it now like the shape of a limason. Next slide. Now, many times we would go into our classroom and we just start teaching, and we do not tell the students that how topics or mathematical concepts are integrated into real life situation. And I thought of, because I have never heard limason, and when I did the research, I had to see how it's actually integrated into real life situation. So, or how it's been applied into real life. So, some ways in which it can be applied into real life is if you have ever seen like a rotating sprinkler, you would see, I know that you know what a limason shape like, you'd actually picture a rotating sprinkler like this here in these pictures here, and you actually see the shape of a limason. Also in art and design, many people created beautiful designs that is being sold for thousands of dollars, and like this one here, and we can see it's being shaped like a limason. Also, it's being applied in toys or machines. If we have ever seen a little ducky like this here, we would see also a limason is here where you can wind it and the ducky would actually move and so on. And there are many more application of limason in real life situation. So looking at the types of limason, you have the inner loop limason, you have the dimple limason, cardioid limason, and the convex limason. Now we're gonna look at the inner loop limason. An inner loop An inner loop limason is a type of limason curved in polar coordinates that has a smaller loop within its larger loop. So for example here, we see that this limason here, you have a larger loop and then you have a smaller loop inside. So this is what you call an inner loop limason. And the equation of an inner loop limason will have the form of A is equal to plus or subtract B cos theta, or R is equal to A plus or subtract B sine theta. And for us to know if it's an inner loop limason, and we'll show this in an example shortly, if B is more than E, then it's an inner loop limason. That's one of the main feature we should look at when we are attempting to solve problems as it relates to inner loop limason. So we're gonna look at graphing inner loop limason. For example, we're gonna graph the inner loop limason of R is equal to 1 plus 2 cos theta. Now, in this case here, A is equal to 1 and B is equal to 2, and B is more than A. So we can see that it's an inner loop limison, and now we can go about and graph the limison. Now, before we graph the limison, we have to compute a table of values. Now, you can choose values from either 0 to 2 radians, or what we might say you can use radians, or you can use 0 degree to 360 degrees. So 2 ways you can compute the table in order for you to graph the limison. You can either use radians or you can use degree. Also, what you need to do too is to use intervals. Sometimes you can use intervals of 30 degrees, 60 degrees, and so on. Now, in this case, we will use degree and interval of 60. And I choose 60 because if we use 30, it's going to be a very large table. So I just decrease it. So here you have the degree, you have cos theta, and we're going to show the work in here as it relates to r is equal to 1 plus 2 cos theta, and then we're going to find the value of r, which is the radius. So where we have 0 degree, and we have 0 degree is 1, as it relates to cos theta, we're going to just plug in 1 here. So we'll plug in 1 where cos is, and you'll have r is equal to 1 plus 2 into 1, which will give us 3. And we continue throughout like that so we can have the values here. And once we have the values here and we have the degree here, we can now plot the graph. Now, we can plot the graph manually as well as through the Desmos. And we'll show you both ways, because what if there's a question in the test and we are not allowed to use application like Desmos and so on? We need to know how to plot it manually. So these are the points. So these are the points we'll be using along with the degree. So on this table here, we have the degree and we have the radius, and this is what we call a polar grid, right? Now, if you see it have both in radians and in degree. So we will, because this table was being done in degree, we'll plot it in degree. So here, you'll have 1. Here, you'll have 2. And here, we'll have 3. Now, for 0 degree, 0 degree is here, you'll have 3 here, right? 60 degree, you'll have 2, which is here. 120, you'll end up with 0, which is the origin here. And 180 is -1. Now, in polar coordinate, a -1 or a negative radius means you plot the point in the opposite direction, which means that if this is negative, it becomes positive. So the 180 degree, which is here, it becomes a positive 1, which is here. Then you have 0 to 40 degree to 0. It comes back to the origin here. And 300, you have 2. So we can plot the graph now. Have something like this, and we see a little loop here. And that's it. That's how you do it manually. Just a slight mistake. This 2 here, the 300, the 2 has to be here. This 1, this 2, so the 300, 2 should have been here. My mistake. This would have been right through here. Sorry about that, sir. Any question? All right. Next slide. And when we put it in decimals, this is what it looks like. So the next thing we're going to move on to is the area of inner loop limison. Now, the formula to find the area of a inner loop limison is the area is equal to half the integral of r squared from theta 1 to theta 2 with respect to theta. And we're going to show you an example. So what is the area enclosed by the inner loop of the given limison by the equation r is equal to 2 plus 4 cos theta? Now to verify, we need to verify if it's an inner loop limison. So the general form is r is equal to a plus b cos theta, where a is equal to 2 and b is equal to 4. And since b is more than a, so 4 is actually more than 2, the limison has an inner loop. So now we can go about and find the area. So you find the bounds of the inner loop where r is equal to 0. So r is equal to 0, which will equal to 2 plus 4 cos theta. So cos theta is going to equal to negative 2 over 4, which is going to equal to cos theta is going to equal to negative 1 over 2. Now, you have to find the values of theta where the limison intersects the origin. So we can integrate after. So the values of theta where the curve crosses the origin are theta 1 is 2 pi over 3 and theta 2 is 4 pi over 3. Now, I don't know how many people can see here. This is where it intersects the origin. But if we look up, 2 pi over 3, we've seen 2 pi. What probably later when the presentation is being sent, you guys can zoom in. If you see carefully, it comes straight here where it intersects here, this line here. Comes straight here where it intersects here. Sorry, my line is not straight. I'm using the mouse. And then you have here coming straight here. This is where two intersect with each other at the origin. That's how we have theta 1 and theta 2. Next slide. So we're going to find the area of the inner loop. So you have half the integral of 4 pi over 3. Sorry, 2 pi over 3 to 4 pi over 3 into 2 plus cos theta all square with respect to theta. You expand here, and this is what we have. And we will use identity for cos squared theta. And the identity for cos squared theta is equal to 1 plus cos 2 theta divided by 2. So substituting this into the integral, you'll have this here. So do I need to say each term or that's okay?
I didn't hear that. What were you asking?
No, I was saying I substitute and I have this. I don't have to pronounce each term or say each term.
Um, you want to know how to read this?
No, sorry, it's okay.
Okay.
We'll move on. The next slide. After substituting, we'll integrate by parts or partial integration. So we integrate this first part here, which is 12 with respect to theta. And we'll have this here. Then we integrate the second part, 16 cos theta with respect to theta. We'll have this here. And when we integrate the third part, we'll have this. And then we put it together, and then we'll have the area of the inner loop limison. Now, actually, the next one is the dimple limison, and it takes the same steps in the same procedure as the inner loop limison. to find the area and so on. We'll just walk you through that. A dimple loop limestone is a type of limestone curve characterized by a shape resembling a circle with a slight dent or dimple on one side. So if we look here, we'll see this limestone here, this dimple loop limestone, you'll see a slight dent. Sometimes you have to look carefully at some of them for you to see the dent, right? And the equation of a dimple limestone will have the form of R is equal to A plus B cos theta to A plus B sine theta. And also one of the features that is important that we need to look for in a dimple limestone is if B divided by A is less than 1, then we can safely say that it's a dimple limestone. And we're gonna graph one of the dimple limestone. So we're gonna graph R is equal to 2 plus cos theta. So in this case, we know A is 2, B is 1, and since half is less than 1, then it's a dimple limestone. And in this case, again, we choose 60 degree, so the interval of 60 degree. And we have the degree, we have the table with the degree cos theta. And we show the working of R is equal to 2 plus cos theta, and then we have R. Same thing, we substitute here for what is cos theta, and we work it out, and we'll have for R, and that's what we do for the rest. So we'll have the degree, for example, on this table here, we'll have the degree, and we'll have the radius, and then we'll plot it. So for 0 degree, so let's see, we have 1, we have 2, and we have 3. So for 0 degree, we'll have 3. We'll have 3. For 60 degree, 60 degree, we'll have 2.5, which is here. For 120 degree, we'll have 1.5. 1.5, this is 1.5 will be here. For 180 degree, we'll have 1. 240 degree, we'll have 1.5. This is 1.5. 300, we'll have 2.5. And then 360, we'll have 3, which is here. So draw. Sorry, I can't draw. It's supposed to be a circle, and then you'll see a slight dent here. Slight dent. And that's how you plot it manually. Yes, here. This was done in Desmos. You'll see a slight dent. As I said, sometimes you have to look carefully to see the dent. Next slide. And then we'll find the area of a dimple limestone. So we're gonna find the area of a dimple limestone, which is, we're gonna use R is equal to 2 plus cos theta. And the formula is half the integral of R squared from theta to 2 pi with respect to theta. So we expand here, we place here, we're gonna have this here. We expand it, we'll have this, write it here. And then we're gonna use identity for cos squared theta, which is 1 plus cos 2 theta over 2. We substitute into the integral, we'll have this here, and we simplify this part here. We have this, and the same step we integrate by parts or by partial integration. So when we integrate the first term, we have this. When we integrate the second term, we'll have this here. Third term, we'll have this. And we take all three parts and we add it together, we'll have 9 pi over 2, which is approximately 14.137 square units. And that's my part of the presentation. My other colleague will continue with cardioids.
Thank you, Miss. Good afternoon, everyone. Yes. So I will be presenting on cardioid, and the name cardioid, it comes from the Greek word cardio, meaning heart. So I have a little demonstration for you. Miss, can I share my screen, please? Can everyone see? Look, so here is, it's sharing? Yeah, so
We can see
here
now.
is our card. Here is how a cardioid is formed. It is defined as the locus of a point on a circle rolling around a fixed circle of the same size. And we can see that. Now, upon completion, we can see that it's a heart shape. Now, de Castellon officially named the heart shape for cardioid in 1741. So this is just a little demonstration as to how it is formed. Yeah. Next. So here we have the formulas that produce the graph of a cardioid. They're given here by R is equal to A. So we have plus or minus. As you can see at the bottom, I have four diagrams there. So it's plus or minus B cos theta, and R is equal plus A plus or minus B sine theta. Now, if you look at the bottom of each graph here, you're going to see the orientation. The first one, yes, the first one here, we have R equal A plus B cos theta. And because of this plus sign, we can see that it is going to the right direction, to the positive side, well, on the for the horizontal. So and the second one is going for the negative side, which is left. So the polar equation of the horizontal cardioid is R is equal to A plus or minus B cos theta. Now, looking at the two last one here, we have a vertical representation, and the polar equation of the vertical cardioid is where we use the sine function. R is equal to A plus B sine plus or minus B sine theta. So here are the let's okay. So here we have some features of cardio. Okay. Okay. So in this one, we have the equation type. Now, something we must note about cardioid before I move on is that the formulas produce the graph. And we have where A is more than 0, A and B is more than 0. And Miss, can you please go back to the previous slide? Because I'm not. The previous one. So here we have A and B is more than 0. And in order for us to produce the cardioid graph, A must be equal to B. So when we divide A by B, we will have 1. A must be equal to B in order to form the shape of a cardioid, and this is how you can identify the cardioid from the equation. Now we look at the features. So looking at this, like we just learned, is that when we have the trig function, when we have cos theta, the cardioid is being in a horizontal direction. So the equation type is R is equal to 1 plus cos theta. Obviously, in the diagram there, or from the equation, we could see that A is 1, and well, B is not. We cannot see that it's 1, but it's understood that 1 is there. So because A is equal to B, we know that the shape formed there would be a cardioid. As you can see here on the diagram. Yes. As you can see here, it's open up to 2. That's the maximum radius. And how we find that? We add A plus B. So 1 plus 1 will be equal to 2. So from the center, straight out, we would have the radius, which is a maximum radius of 2. And as we can see, it's symmetrical along the horizontal axis, which is the x-axis there. And lastly, because it's positive, it's open to the right. So we have some application of cardioid in real life where you can see there's a picture there of a microphone. So cardioid microphones are known for their directional pickup pattern, making them effective in isolating sounds from a specific direction, useful in interviews, podcasts, and other situations where background noise needs to be minimized. So here we could see the use. And of course, as we're doing it right here in maths, and probably as we go further, our advanced physics, we can come across it again. So sketching the graph of a cardioid. So we have here, R is equal to 2 plus 2 cos theta. So this is a polar equation. So this is a polar equation where R is the radius or the distance from the origin, and theta here is the angle from the positive x-axis. So the shape of the graph that results from this. And how do we detect the shape? We look at A being 2 here and B being 2. So when we see that A is equal to B, or when we divide A by B, we have 1, 2 into 2 is 1. We know that this equation here produces a cardioid. So these are stuff that we need to check first. So the equation first is tested for symmetry, and polar graphs can be symmetric about 3 places: the polar axis, which is the horizontal axis like I just showed you there, the line theta, which is equal to pi over 2, which is a vertical line, or the pole, which is the origin. So since R is equal to 2 plus 2 cos theta. It involves cos theta, which is symmetric about the polar axis or the horizontal axis, so we know that. And all of these we need to know before we just go ahead and sketch. The graph will be symmetric about the horizontal polar axis. This helps us to sketch one side of the graph and then we can mirror it. So Miss in her previous presentation, she would have highlighted some of that. So first we find 0. You set R is equal to 0 to find when the curve touches the origin. So 0 is, so we put 0 there. So it's equal to 2 plus 2 cos theta. And cos theta is equal to 1. Now, here we would know the range that from this we would know the range that we will be using. So it would be from 0, which is the origin, to pi. So the most relevant angle in the interval is 0 to 2 pi. And theta is pi, given the point 0, pi, which lies in the origin. So now we're gonna find the maximum value. So we need to know how far this cardioid is going. So you substitute where is the theta, you put 0 into the equation and solve for R. And we know that from just now, we know that cos theta or cos 0 is equal to 1. So 2 plus 2 multiplied by 1 is equal to 4. So the maximum point is 4, 0. So, however, even though the graph is symmetric, we still need to evaluate and plot points from theta equals 0, from theta equals 0 to theta equal to pi to fully understand 1/2 of the graph. So we can reflect it over the horizontal axis to complete the graph. So here we have the table of value and where theta is, so R is equal to 2 plus 2. So we have R is equal to 2 plus 2. And here we have 0, theta is 0. So cos, please excuse me, I'm using my mouse. Cos 0. So cos 0 is equal to 1. 2 times 1 is equal to 2. And 2 plus 2 is equal to 4. So that's how we end up here. And where we see theta here for cos theta, you substitute pi over 4. We're going to have 3.41. Where we see pi over 2, when you substitute and work it out, you're going to have 2. And so on. And as we could see here, as Miss had demonstrated earlier, on the polar grid, we could plot the points the same way. Okay, so now okay. So let's see in Desmos. So here we have the cardioid. So as we could see in the equation here, 2 plus 2 is equal to 4. Look on the graph here, from the center, from the origin, the cardioid is extended, so this is the maximum radius here. As you can see here, it's 4. Now let's see what happens. Let's see what happens when we add. So let's try R is equal to 2 minus 2 cos theta. So because we have 2 minus 2 cos theta, it flips to the other side, to the opposite direction, to the left. Let's see what happens when we double it. So we have R is equal to, say, 4 plus 4 plus theta. And you see here, it increases its size. So these numbers here, they tell us how large or small it could be. And remember, A and B must be more than 0. And the sign in the middle will tell us the direction it's going. Now, what if we change from cos to sine? See what happens there? The orientation changes, so vertical. Okay, so we'll move on to the area of cardio. You know, Miss BB would have already explained this. Everything that we're presented on, it is somewhat related. So here we have the area of, finding the area of cardio. We have R is equal to 2, the bracket 1 plus cos theta. So we need to find the area of that. So the first thing we do is that we square the function. That is a first step. Square the function. So when we square this whole function, we're going to end up with 4 open bracket 1 plus 2 cos theta plus cos squared theta. This by multiplying that. The formula to find area in polar coordinates, the next, is equal to, the area is equal to half the integral of r squared from 0 to, of r squared from 0 to 2 pi with respect to theta. Now here we plug it into the formula where you see r squared. Remember, we would have just square r. So where you see r squared, you substitute it into the formula here. So it becomes half the integral of 0 to pi. And this here 4 open bracket 1 plus 2 cos theta plus cos squared theta close bracket with respect to theta. Now, since the cardioid complete one full loop from theta equal to 0 to theta equal to, that's a limit we're working with, theta equal to 2 pi, we use those limits. So we substitute where we have r squared, we substitute We factor out the 4 here. We factor out the 4, so we have area is equal to 2. When we factor out the 4 here, we're going to have area is equal to 2. The integral of 0 to 2 pi, open bracket, 1 plus 2 cos theta plus cos squared theta with respect to theta. And we use a trig identity to simplify cos squared theta, since we can't integrate cos squared theta directly. So what we do here, we use cos squared theta is equal to 1 plus cos 2 theta over 2. So it becomes 1 plus 2 cos theta plus 1 plus 2 cos theta over 2. So basically what we do in this equation here, where you see cos squared theta, we put in this identity here, as you could see. Next. So we combine the terms. So we have 3 over 2 plus 2 cos squared theta plus half cos theta. We combine it. This is what we have now. We integrate each term. So 3 over 2 with respect, we integrate 3 over 2 with respect to theta. We're going to have 3 over 2 times 2 pi. And that will give us 3 pi. Then we have 2 cos theta with respect to theta. We integrate that, we have 0. Half cos 2 theta with respect to theta, we have 0. So here we have 3 theta times 2 theta is equal to 6 theta. So that this here is the area of the cardioid. We have another example here. Next time we're using sine. So it's the same thing. We have r is equal to 1 plus sine theta. And we look at the equation and we can see that it's a cardioid equation. So we go ahead, use the formula, and where we see r, we put in 1 plus sine theta, as you could see here. Then you expand the term, expand the square term, so we'll have 1 plus sine theta all square is equal to 1 plus 2 sine theta plus sine squared theta. Here we use an identity. So sine squared theta is equal to 1 minus cos 2 theta all over 2. So where we see sine squared theta here, we're gonna put in the trig identity. So it's gonna be 1 plus 2 sine theta plus the trig identity here. And that will be equal to, when we multiply it, it's going to be equal to 3 over 2 plus 2 sine theta minus half cos 2 theta. And we go ahead and integrate each term in r square here. So we have 3 over 2, like we just did. It's going to be 3 theta. 2 sine theta with respect to theta is going to be 0. When we integrate half cos 2 theta with respect to theta, we have 0. So half times 3 theta is equal to 3 theta over 2. And that is the area. Okay, so final. Next, we're going to look at the convex limison. So what makes a limison convex? when the value of A is greater than or equal to the value of 2B, the graph is a convex limison. So as you can see here, this is how a convex limison is shaped. It's a circle with one side flattened, as you can see over here. This side is flattened. And it says here that when we divide A by B, we must have a value more than 2. So as you can see here, A is more than B. So when A is more than B, it's a convex limison. So the general polar equation of a convex limison is R is equal to A plus B cos theta, or R is equal to A plus B sine theta. With the conditions is more than B is more than 0. So this condition ensures the limison is convex, meaning it has no inner loop or dimple. The graph looks smooth and rounded, kind of like a slightly distorted sphere. So it's basically the same step as we did with cardioid in finding the area of a limison. So the first thing we look at our equation here, we can see that A here is more than B. So therefore, since A is 3 and B is 2, and A is more than B, it's a convex limison. We go ahead and we put it into the equation and we square R. When we square R, we're going to end up with 9 plus 12 cos theta plus 4 square theta. 4 cos square theta. And we plug it into the area formula. Now the area formula here, we have R squared. So where is the R squared? You substitute it with this. Next. And we use identity for cos squared theta, which is 1 plus cos 2 theta all over. So where you see cos squared theta, insert that, so it's going to be 4 cos squared theta is equal to 2 plus 2 cos 2 theta. So the integral becomes half the integral of 0 to 2 pi. And this is what our work out to be with respect to theta. When we simplify it, we have half the integral of 0 to 2 pi is equal to 11 plus 12 cos theta plus 2 cos, open bracket, 2 cos theta with respect to theta. We integrate each term. So when we integrate 11, we're going to have 22 pi cos theta 0 cos 2 theta 0. We plug in and simplify, so the area is equal to half, open bracket, 22 pi plus 0 is going to be half of 22 pi, which is equal to 11 pi. Next. So let's see our limit, our convex limison looks. So there we have R is equal to 3. Remember, A is more than B. 3 plus 2. So as you can see here, it's a flattened circle. And that's how it looks. And it's the same thing with the cardioid in terms of the orientation. We have R is equal to 4 plus sine paper. As you can see there, it's the same thing as cardioid because it goes in a vertical direction, and sine, the cos in a horizontal direction and sine in a vertical. Next person.
All right, good afternoon. Myself and my other colleague will be looking at spirals. Imagine you are a point moving away from a central spot. Now, instead of just moving in a straight line, you start turning around that central spot. Now, the path that you trace, it can often be a spiral. So the definition we have is spiral is a curve that starts at a central point and winds outwards or inwards, like a coil or the shell of a snail. In polar coordinates, a spiral is described using a formula that relates r, which is the distance from the center or the origin, and theta, which is the angle from the positive x-axis. Now, we're going to look at some types of spiral. In this presentation, we have 3 of them. The first one we have there is the Archimedean spiral. Now it states the Archimedean spiral is a type of spiral that is commonly used to describe shapes like a snail shell when the turns are evenly spaced. Now the general equation for the spiral, we have r is equal to a theta. It is called the Archimedean spiral because it was studied by Archimedes. And here we have some examples. We have the snail shell here, and this here is how it looks. Now, the r will be the distance from the center to any point on the graphic, on the spiral here. So this line here will be the r. Now, graphing the Archimedean spiral, like my other colleagues did, we can graph it manually. We have to form a table. And that table, you'll have your theta and you'll have r. Now we want to sketch the graph of r equal theta from 0 to 2 pi. So we can use 0, pi over 6, pi over 3, and so on until we reach 2 pi. Now these figures here for r, you just put in pi over 6 into your calculator and you'll have these figures here. So we can go ahead and plot them. For the first one, we have 0, 0, which is in the center here. The second one, we have pi over 6. And that there goes to 0.5. So this is 1, this here will be 2, 3, and so on until you reach to 5. So 0.5 will be somewhere here in the middle. The next one, we have pi over 2, pi over 3, which is 1.1. So 1.1 will be somewhere here. And then we have 1.6 for pi over 2, 1.6, and it goes on, right? So this spiral here will look something like this here, right? It keeps going, going, going. So that there is how we can graph it manually. Now, we can also graph it using Desmos to show you how exactly the spiral will look like. Good. So here we have the equation r is equal to 8 theta, and we get from the range from 0 to 8 pi. Now, as you can see, when I move this a here, the value for it, if I increase it, you see that the spiral, it gets bigger and bigger. So the a will tell us the size of the spiral. If we go to the negative side, you see the spiral, it opens in the negative direction, right? Positive, you see the spiral, it opens to the positive side here. So the spacing between each one of these circles here, they are the same for the Archimedean spiral. So from this point to this point here, it's the same distance as the second one here, right? But after that, we go on to the area of the Archimedean spiral. We have example 1. Find the area swept out by the Archimedean spiral r equal theta from theta equals 0 to theta equal to pi. Now the general formula for the area, we have area is equal to half the integral from alpha to beta of r squared with respect to theta. Now the r is theta, beta is 2 pi, and alpha is 0. Now we go ahead and we plug those values inside our formula. We'll have a is equal to half the integral from 0 to 2 pi theta squared with respect to theta. When we integrate theta squared with respect to theta, we have theta cubed divided by 3. Next step, we can go ahead and work out this square bracket for the range theta 2 pi to 0. So we'll have area is equal to half multiplied by 2 pi cubed divided by 3 minus 0 cubed divided by 3. Now this 0 over 3 will cancel out, so we're left with area is equal to half multiplied by 8 pi cubed divided by 3. That there will give us an answer of 4 pi cubed over 3, and that there will be our area. This here is the diagram. The shaded part here will be the area that we just found. The second one, we have find the area swept out by the Archimedean spiral r equal to theta from theta equals 0 to theta equal pi. The same steps we do again. We have the formula. R half of integral of alpha to beta r squared with respect to theta. Here we have r is 2 theta. So when we square it, we'll have 4 theta square. We go ahead and we substitute those values inside our formula. We'll have half times 4, the integral from 0 to theta squared with respect to theta. When you multiply that there, we work it out, we have 2, the integral from 0 to theta squared with respect to theta. When we integrate theta squared d theta, we have theta cubed divided by 3. When you go ahead and work out that, you'll have area is equal to 2 multiplied by theta cubed, pi cubed, divided by 3 minus 0 cubed divided by 3. Again, the 0 over 3 will cancel out. So we have the area is equal to 2 multiplied by pi cubed divided by 3, which will give us an answer of 2 pi cubed divided by 3. So here, the shaded part here is the area that we just found. The next type of spiral we'll be looking at is the logarithmic spiral. Now, it states the logarithmic spiral is a type of curve that winds around a central point, getting farther away as it rotates. but the spacing increases exponentially. We have the general equation for the formula, which is R is equal to e to the 8th theta power. Now, the R is the radical distance. Again, at the bottom here, R is the distance from the center to any point on the spiral here. We have theta, that there is the angle, and it is measured from the positive x-axis. So it will be from the positive x-axis here, and it goes around anywhere here. And A, we have is a constant that determines how tightly or loosely the spiral winds. If A is more than 0, the spiral will expand outwards. And if A is less than 0, the spiral will contract inwards. We have E from the formula here, that there is the base of the natural logarithm, and it is approximately 2.718. Right? We have some examples of the logarithmic spirals. We have hurricanes and we have galaxies. Now, if we want to graph it manually, you have to get your table. You'll have theta, then you have your function, which is e 2.2 multiplied by theta. In this case here, we want to sketch the graph. R is equal to e 0.2 theta. So all you do now, you just insert your figures into this formula here, and you'll get your values for R. So for the first one, we have 0, 1. Again, here is 1. Here will be 2. Here will be 3. And here will be 4. So the first one, we have 0, 1. So 0, 1, which is here. Next one, we have pi over 6, which is 1.1. Pi over 6 is here, that is 1.1. Then we have pi over 3, which is 1.23. 1.23 will be somewhere here. Then we have pi over 2, which is 1.37. Pi over 2, 1.37. Then we have 2 pi over 3, which is 1.52. So 1.52, let's say it's somewhere here. And we have 5 pi over 6, which is 1.69, which is somewhere here. We have 7 pi over 6, which is 2.08. So 1, 2. Oh, sorry. Yes, so we have, oh, sorry, pi is 1.87. 1.87 is here. Then we have 7 pi over 6, which is 2.08, and it continues, right? I won't draw it out. So the spiral will look something like this here. And then as we continue it, it will get bigger and bigger here, right? So it looks, sorry about the drawing, I'm using the computer, it doesn't draw that well. I'll show you on Desmos as well how it actually looks. Good, so the Desmos. But here we have the spiral. We have R is equal to E to 8 times theta power. So we get the range from 0 to 8 pi. Now, Okay, you can see it a bit better there. Good. So if we're going to move A, let's move it a little. We see that this spiral, it keeps on getting bigger and bigger, right? That's towards the positive side there. If you move it towards the negative side, I'll have to zoom it up. Yeah, we move it towards the positive side, you can see that the spiral, it goes inwards, right? That's the negative, it goes inwards. And when we move it towards the positive side here, you see it goes towards the positive side, sorry, right? So the spiral opens toward in the positive side. All right, I'll now hand you over to my next colleague who will do the example.
Good afternoon, everyone. My name is Divya Kiswanram. I'll be looking at the area of the logarithmic spiral. So the example goes, find the area swept out by the logarithmic spiral r equal to e to the power 0.3 theta as theta goes from 0 to 2 pi. So the general function or formula for the area enclosed by a polar curve, such as a logarithmic spiral, is a half the integral from alpha to beta r squared with respect to theta. So this is the general form I'm talking about. And here we have a graph displaying the logarithmic spiral. As we see in yellow here is the area which we will be finding. So we substitute all our values here into this formula. And we integrate it e to the power, sorry, colleagues, r equal e to the power 0.3 theta. When we square it, we have e to the power 0.6 theta. And we substitute all this value here into the formula. Then we integrate e to the power 0.6 theta, and we'll have this. After we integrated, the next part is evaluating the definite integral from theta equal to 0 to theta equal to 2 pi to find the area. Excuse me, we found the integral of e to the power 0.6 theta to be 5 divided by 3 e to the power of 0.6 theta. Now we will evaluate the expression from theta equal to 0 to theta equal to 2 pi, which is here. Now we multiply. So 1 times 5 will be 5, 2 times 3 will be 6. Now we multiply the beta and the alpha. E to the power of 0 would give us 1. Will give us 1, and then we can simplify this part. So e to the power of 1.2 pi, we can use pi as 3.1416, and 1.2 pi will give us approximately this. We can put e to the pi that we figure out, which will give us approximately something like this. And then we will simplify, and the area will become 35.355 square units, and we can round it off. So the area that we found is 35.36 square units. Let me erase this, please. Now, a hyperbolic spiral is a type of spiral curve that moves inwards and towards the center as it turns, instead of outwards like most spirals. The general equation for this spiral is R equal to A over theta. So our R, give me a second. So our R is the radical distance from the origin to a point on the spiral. Our A is the constant that defines how tightly the spirals wrap near the origin. And on the graph, we can see how the spiral gets tighter as it approaches the center. And in shortly, I'll show you a demonstration on this more on how that shows. So next slide, please. So as the value for theta increases, the hyperbolic spiral winds inward towards the pole. The radius gets smaller and smaller, but the curve never actually touches the center. But the curve never actually touches the center and it spiral infinitely close. On the other hand, as theta approaches zero, the spiral stretches outward or outway from the pole with the radius becoming very large. Now for the area of the hyperbolic spiral, a particle moves along the hyperbolic spiral defined by the equation R is equal to 5 upon theta. Find the area swept by the spiral as the particles move from the angle theta is equal to pi over 2 to theta equal to pi. So the shaded part in the graph is actually where we're going to find the area. So the general formula for the area enclosed by a polar curve is half the integral from 1 to 2 of r squared with respect to theta, which is this. We square the polar function, the 5 theta will become 25 over theta squared. We set up the definite integral and we substitute this into the formula. Now we have 1 or a half the integral from pi over 2 to pi of 25 over theta squared with respect to theta, and we factor out for step 3, we factor out the constant. We can take out the 25 out of the integral because it's a constant. So now we have 25 over 2 of 1 over theta squared d theta. Then we subtract the fraction. 1 over theta plus 2 over theta will give us 1 over theta. And finally, we can multiply the results, 25 over 2. So the final area will be 25 over pi, 2 pi squared. And it will be approximately like 3.398 square units. So that is for example 1. For example 2. Example 2 is calculate the area swept out by the spiral R equal to 3 over theta from theta equal 1 to theta equal to 4 radians. And as we can see in the graph, the shaded part is actually the area, which we're gonna find. Now, 3 over theta will become 9 over theta square. And I apologize for the noise in my background. Theta 1 will become 1 and theta 2 will become 4. Now we substitute that into the formula. The area equal, I have the integral from 1 to 4 of 9 over theta square. We factor out the constant. We can take out the 9 outside of the integral, so because it's a constant, so we have 9 divided by 2 times the integral 1 from 4 of 1 divided by theta square with respect to theta. Then the integral of -1. So now we evaluate from 1 to 4, the negative 1 over 4 plus 1, we'll simplify that to 3 over 4, and we can multiply the results, and we have 27 over 8, which can approximately be 3.375. And after this, we have a small activity for the class to do. So the activity is to identify the types of spirals given below. So we have 4, and out of the 4, we touched on 3 thus far. So we'd like to hear your responses, please.
Hi, good afternoon, everyone. I believe the first one is the logarithmic spiral. The second one, we didn't do it. I think the third one is the Archimedean, and the fourth one is the hyperbolic.
Job well done, Ms. Vivi. Thank you so much. You got all correct. And that is it for our presentation. Thank you, colleagues.
Any observations you all want to make? It's a very passive class, you know. You see how many people? 13? All right, let me make a few observations. I think it's a much better prepared presentation than the last one. Not to make any unfavorable comparison, but I like your coverage of area. I have a comment about area. I think there was an error somewhere. Yeah, a few things. I still feel there should be some more collaboration. I'll tell you why just now. But just go back to this. Who's this person? Whose slides are here? And it started with, okay, go to that third slide where they have a snail, and yeah. Did it look to anybody that the snail doesn't look like the limousin? But it looks more like the spiral?
Yes, sir.
Yes. Where are you seeing this shape, right? Let me go. Where are you seeing this shape on this thing here? Or I'm what I call spatially challenged. The spiral on the shell seemed to be more like the spiral. It's a spiral. It looks more like the spiral you all discussed at the end. It doesn't look like this, and I wonder why. You can see any connection? Why one look like the other? Any thoughts?
Could it be the outer shape on the shell, sir? But I'm still in like on the shell, if you outline the outer part.
Oh, so you think if you outline
Probably like that. But
like this,
looking at it, it would work as a
and then all
spiral.
right. So you don't neglect
it kind of
neglect all
resembles
the
like
whorls and okay, like it come back like that. Okay. You see, it's good to know. Sometimes I remember when you do poetry in school, and a poet uses a certain expression, and here they ask you what probably the person was thinking, and I want to know, how am I going to know? I wasn't there, you know? And I'm wondering whether if you watch the snail from the front, right, like it's approaching you. If you were to take this, sometimes you see they put a tangent here and a tangent there, right, on this thing. And if you were to look at this snail from the front, the shell might very well look like this, right? I need to draw it. Give me a second. Let me just use the, yeah. I'm wondering whether when you look at it from the front, like maybe you look at it from the front. Okay, so it's approaching you like, right? And the body is here somehow. And those whiskers are like, like that. I'm wondering what is it they have in mind? Because it seemed more like the spiral than the limousin. I was a little puzzled myself when you mentioned that bit of history there. Okay, yeah. And what I would have liked to see though is what the last two portions did. I noticed the last two portions. Why is this piece erasing? Oh, I think it's not me. I didn't put this on. Yeah. The last two portions, when they were drawing or demonstrating the equation and the graph, they used that Desmos animation, where they had the slider on the, I think the A value, right? And I wish the previous portions, yes, but this is this portion, yes. But there was another, there were two others before when you did the limousin and the cardioid. I wish that portion, they used Desmos, but they should have put the slider now, right? For A and B, and vary those, and let us see what happens, right? Let us see what happens to the limousin, right? What happens to it? Y'all get what I'm saying? The person who,
Yes, sir.
yeah,
Yes, sir. Because
Yes,
I
sir.
didn't mind I didn't use a slider. I just type in the other equation. So
yeah,
it just show that, yeah.
yes, it's nice, especially for those of us who like to see these animations and so, right? It really helps, right? And that's why I think the other people in your group should have said, hey, why you not do the thing like this, put in a little slider and so, you understand? You don't want the other people say, oh, I hear me won't look nice. I mean, tell you nothing. Your other group, you want to collaborate closely. One last observation. Somebody was doing area under the spirals. Maybe put up the one with logarithmic spiral. Somebody was doing a piece of area. Oh, the one with the yellow shading. There was one, yes. So you are finding the area from 0 to 2 pi. And you think that, well, I notice you share this whole area here as that, right? Let's just do a test case, right? I just want to show you something. So your area that you got is roughly 36, right? 36 is the answer. So what's something here? From here to here is 10, and from here to here is 10. Is how far apart is this? Anybody? How far apart is it? Is it 10? I can't see good. Yeah, okay.
Yeah.
Good. So it looks like 10, huh? This is 20 and that's 30. 0, this is minus 10. So this bit of area here is 100 almost, right? It's 100 already. Anybody getting what I'm saying? So if this area, this whole yellow area, it can be 35 point something. Something is wrong. Y'all follow me? One of this box here is 100 units. That's so 10 by 10.
Yes, sir.
Yeah, so it's not that. It is really if you look back good, it is this little area here. This where is it? 0 to 2 pi. So it's this little area here, this area here. This little area here. That will be that 36 square units. This area here.
Oh, okay, sir.
Yeah, very, very small. And you see, sometimes you got to be sober up and kind of watch that. Wait, this thing is 35 point something. But why then boxing there is 100 square units already? Right? So I think all the others got the same problem. I think. All the other examples, I think, get that problem. Where you don't figure out where really is the area. I think it was easier with the cardioid and so on, the limousin. It was easier because, it's pretty straightforward. What I didn't notice anybody doing in any of the presentation was, like, if you have a cardioid, right? Could you have like a blank spot? Can you go to a slide where I can have some more blank? A blank area to write on? Maybe the last, what about this one here? Okay, yes. I just want to hear about it. You can erase it just now. Like, I didn't notice anybody attempt this bowl thing. I mean, I didn't tell you specifically. I did hint at it as the kind of test questions I gave in the past. So you have let's say you have a cardioid. Maybe, okay, it looks like this, something like that. And maybe if I have a circle in here and I shade this piece, can you find such an area, So you have a cardioid, you have a circle inside the cardioid. And I probably color up inside here. It's not hard. I mean, should be easy for you to find, but I'm just saying nobody attempted that complicated one, Something to think about. All right. Well, overall, I like this presentation a little more. Those are some small little things, right? All right, good. So if there are no more questions, I can stop this recording.